Hello folks, this is Todd Coburn of Cal Poly Pomona with lecture 17b of Aero 3261. Today we're going to continue our study of shear flow in open thin-walled sections, and we're going to look specifically at the delta P method. Let's start by a little beam, and we're going to idealize this beam with the caps carrying all of the normal stresses and the webs carrying only shear stress. We've looked at this idealization a few times. Now let's say that the thing is held at say the back end and is loaded with a shear force on the front as shown. Now since the web is assumed to carry no normal stress, all of the normal stress has to be carried in the caps. Since the caps are assumed to have just a tiny point area with an actual area, but all of that area located in like a specific tiny infinitesimal point, the caps have no bending stiffness, which means they can carry no shear. We're going to look at how to solve shear flow equations using the delta P method. First, we're going to need to calculate the properties of our section. We're going to do that in the normal way. For a simple two-cap member, that's going to be pretty straightforward. We could create a table, or we can just do it analytically. H, we're going to say, is just H1 plus H2, where H2 is locating the CG, wherever that is. So if we define a coordinate system, X and Y, this is our X. We can see our Y coordinate here. That means we're going to have two areas located as shown, and we're going to calculate the areas and their Y bars. We can see the first one is located at H and the second one is located at 0. Therefore the Y bar is going to occur at just H over 2 if these have the same exact area. If they have different areas, they will have a different Y bar. The I is just going to be the sum of the A times the Y minus Y bar squared in the same manner we did before, which simplifies to this. Now we can calculate our unit stresses. So remember, our stress is MC over I, but if we talk about the unit stress, what we're talking about is the change in stress per unit length. So our stress is simply MC over I. If we want the unit stress, we're going to be taking the unit moment, which basically means we're going to take that shear and multiply it by 1 inch. For example, the shear located here, if we multiply it by 1 inch moving this way, that will be the unit moment, the amount of moment that develops per inch due to that shear force. So V times 1 inch is the unit moment. Got that? With that idea, what this quantity, this unit stress, is doing is just giving us the change in stress per unit inch. If we plug in that unit moment, which is just V times 1 times our property C and our I. This simplifies to this, and we find this relation. Now if we want to turn that into a force, we're just going to multiply that unit stress by the area, and that gives us the force per unit inch, or the change in force, which really is like a shear flow. It's a change in force per unit inch. So that's just V over H. Now we could have come to the same conclusion through statics alone, because if we look at a side view of this, we've got a cap here, and we've got a cap here, and we've got a web, which we're assuming carries no normal stress. If that shear is applied here at this end, and if this dimension is 1 inch, then the moment on the other end, this moment, is going to be V times 1. Now if we want to know how much force, by statics we can sum the forces about here, and we find moment, which is V times 1, is equal to, and we can see this is going to be a compressive reaction here and a tensile reaction here. So that's going to be equal to P times H, right? That's going to be the moment to that end. That means that little P, which is actually a delta P since it's per unit inch, is going to be equal to V over H. The same exact thing that we found here. If we now sum our forces in the X direction, that has to be 0, and we find that P minus P equals 0. Therefore, this P down here is equal and opposite to that P up there. So we could have found this relation through statics, or we can calculate the stresses as we did here. Okay? Now this is actually, we're going to find this is very powerful. Continuing on, we now can draw a little free body diagram. So what we're doing here is we're taking a little infinitesimal piece. We're going to focus on a little piece right here, and we can say, well, if the shear was applied at this end, then, well, there's no axial load in the piece here, but at the far end, now we're going to have that force times this dimension here, which we said was 1 inch, is going to be what this little reactionary force, that delta P over here, is. Right? That's what we just calculated. This is giving us the delta P there. In fact, it's very useful to actually draw this before continuing. Here's our piece with a little unit piece like this, and what we have here is a delta P there and a tensile delta P here. Now, having done that, we now can make a little section cut along here as we're doing here, and we can now sum our forces in this direction, which means Q times that distance 1 minus delta P equals 0. So we find that the shear flow in the web has got to be delta P. In fact, it's pretty obvious. If this is acting on this end of the rod or the cap, and this end has no force continuing through the member, this shear flow better completely react what's happening here. So we can see this method allows us to immediately determine what the shear flow is in our web. Now, when we had a thick continuous web, we would take the Q of that. Remember that? We take the A and the Y bar. But remember, in our case, now with this idealization, this thin web idealization, we're assuming that the webs themselves carry no axial load. That means they have no area for the purposes of resisting normal stresses. This means that once you calculate the shear flow in the web, the only thing that will change the shear flow in the web are these point lumped areas, and then the shear flow will be constant. So what that means is now that we know what the shear flow in this web is, here we saw that since this is delta P, this is Q, and this is Q, and this is Q. If we had drawn more of it, we would have got the same thing, right? If this is delta P, this is going to be Q, and so on, and this is going to be acting on this face, and this is going to be acting on that face. If we had drawn even more of it, come all the way to the bottom, just before we hit that upper cap, that little delta P here is reacted by this Q, the same Q, and you can see that's generating a shear flow like that along that edge, and like this along this edge. Okay? So we sum our forces in that direction. Q times 1 minus delta P is 0. That means Q is delta P. We saw that, which means it's the same result as we saw before. Alternately, we could have summed our forces and done the exact same thing. Now, because we have only a web, if we look at this part again, what we have are two normal areas and something that has shear resistance. Remember, these caps have normal resistance, but they have no shear resistance. So if we had instead summed our forces in the y direction, those must be equal to 0, we would have said, okay, we've got a shear like this, and it's being reacted by the shear flows which must be resisting it. That's Q. And if this is H here, then the force, let's see, V is acting up, so V minus Q times H has got to be equal to 0. That means our shear flow is just V over H. That's another way to solving this, because this only has 2 rods. So really, this is probably the easiest way to solve this, but when we have more rods, more areas, a more complicated section, we're going to find that this delta P method that's defined here is much easier to use than most of the other methods we might have. And that is the power of the delta P method. Let's look at an example. Here is another lumped beam. We have 4-point areas, and these are the areas of each of those. And we have various web thicknesses. Now in this particular case, since we have more than 2 areas, more than 1 web, we're going to actually need to apply something more complicated than just summing vertical forces. And the easiest way is the delta P method. We're going to start by creating properties of our section. We construct our table, put in all of the areas, put in the X and the Y positions from a reference axis. This is assuming, in this case, as usual, we're going to pick a lower corner, and we will say, okay, we'll call that X. We'll call this Y. Therefore, our X and our Y position. So stringer A, as it has an area of 2, it's at 0.16. Stringer B is at 4.16. Stringer C is at 0.0, and stringer D is at 4.0. Got that? So having done that, we now can calculate our properties by constructing the rest of our table. We get our X bar and our Y bar and our moments of inertia about the various axes. Now you'll notice this particular shear is causing a moment about the x-axis, so we're going to only need the I about the x-axis to solve this problem. And if we continue our solution using our positive beam sign convention, we can calculate the stress. Actually, we can do it directly in this table. mx over its I minus my over its I, and the y minus y bar and x minus x bars give us the total stress. In this case, we only have a mx, and since we're going to use a unit moment, it doesn't matter how long this beam is. We're just going to take that v times 1 is our unit moment. If that's our stress, our force in any cap will be that stress times the area. So we can calculate the change in force like this. Our moment is just 1 times v, and we can put another little column here to deal with all those calculations. Often it's actually more convenient to have 2 columns, 1 column for the unit stress change and another column for the unit force change. That will make it easier to keep track of. We then can walk through the segment one piece at a time, and the way we do that is like this. We pick a free edge like this one down here, and we draw our delta forces. In fact, it's actually useful to first draw all of our little unit areas, and from this column of the table we'll put what they are. So at area C we've got tension, so we'd put our little tension 250, and at A we have compression. That's this 250 of compression going like this. The next one's all in compression also, and the next one's in tension. Then we draw a little free body diagram of this first element with our little change in force from 1 inch to the next. That's the change in force, and the shear flow will react against it. That's our shear flow, which means this is tail to tail and this is head to head. Therefore, we can calculate this flow is just going to be equal to this shear flow is just our 250. And we can see if it's going back into the page here, equal and opposite means it's coming out of the page here, which means that all these are going down and this is going back. This is the same shear flow. We haven't passed any areas, so that hasn't changed. And That's the equal and opposite here. That still hasn't changed. So when we do a free body diagram of this, now what we have is Q in web AC. Remember that Q through there is a constant, and we have Q in web AB, both acting on it. We see that this one's going against the force, and this one looks like it's going in the same direction. We just assumed that. So what we're going to do is sum our forces in this direction. Let's call that positive. That's got to be equal to 0. So we're going to have delta P at A minus QAC times 1 plus QAB times 1 equals 0. And with that, since this is 250 and this is 250, they cancel, and we find that the shear flow in web AB is 0. Then we have equal and opposite, equal and opposite, equal and opposite, head to head, and now we do the same thing here. Or you could just look at it. You can continue working through the problem this way, or just look and say, hey, by symmetry, these numbers are going to be the same. Okay, now here's another problem. This has only 2 axial caps, and we have a unit moment. Now you'll notice we have a pure moment, there's no shear. What that means is that while this moment will cause stresses in the caps, those stresses will not change along the length of the beam. It's going to be constant. We can solve this by calculating our properties as we have before, calculating our area, our y-bar, and our moment of inertia. We then can apply our stress equation to calculate what the stresses are in each cap and multiply those stresses by the corresponding areas to get the forces in each cap. Now you'll notice these forces are equal and opposite, right? As they should be at this point. And if we went 1 inch into the page, since this is a pure moment, there's no shear on this beam, we'll have exactly the same forces. What this example is doing is teaching us how to plot this out with what's called an exploded free body diagram. So if we look at our beam, this is what we saw before. The other picture was actually looking at the end of it. What we saw was our 2 lumped areas before, as shown over to the right. Now, if we want to draw an exploded free body diagram, that means is we're going to take each element of the beam, blow it apart as if somebody had exploded the thing, and then we're going to put our forces on it and work our way through the structure to figure out what all the forces and all the members are. Okay, so we start off by grabbing the results from the last slide where we have the areas and the forces. And then we're going to draw an exploded free body diagram, and then we're going to start plotting our forces on it. So we're going to start by looking at the upper cap. We know that that moment on one end of the beam caused a force. We calculated the force at one end, and that's that P on the right side. And because this is a pure moment, there's no shear, we know that the force on the other end of it will also be P. Now, because there's a web attached and webs actually have shear resistance, that means since we cut the web off, we're going to replace it with a shear flow acting along there. So the total force due to that shear flow would be that shear flow times the length W. However, since the force at the right end and the force at the left end are equal and opposite, that means the shear flow will be 0. If we sum the forces in the x direction, we'll see P minus P plus QW is equal to 0. That means Q is 0 since W is not. Now we draw our next little piece. We can draw the lower cap. That was P, 90,000 pounds of tension. And the same thing's true since the same force is on both ends, equal and opposite. That shear flow along there will be 0 as well. If we draw the web, we can say, well, the top web going in the opposite direction, we draw those arrows in the other direction. And at the bottom, remember the web has remember that the web has a constant shear flow. This means once we calculate the shear flow anywhere, the whole web is carrying that shear flow. And we can see from the upper cap to the web, that's switching the directions, equal and opposite, action and reaction pairs. From the web to the lower cap, same thing. And because shear flows are so romantic, once we know what the direction is for any web, any spot on any web, we know what all the rest of the directions are. head to head, tail to tail. Now we're ready to draw our vertical stiffeners. We've got one over there and one over there. And we can see that the shear flow along there is 0, and that would correspond with any shear. Now in this particular case, we found our shear flow is 0, therefore our force will be 0. If we had just summed our moments, P times H is equal to the moment, we would have gotten the same thing. And we said that. Okay, now we've got another example here. This is a cantilever beam with an axial force. Now in this case we now do have shear, which means we are getting the moment to change from one spot to the next. Now our moment 900 is actually from this force. That's the moment at A and B. So obviously the moment at CD is 0, the moment at AB is 900 inch kips, and everything between there is changing linearly. Now this would have been solved. Now we still have a moment, but now we also have a shear. We would have gotten the exact same numbers in the caps before, and if we draw our exploded free body diagram, it would look something like this. We'd start off with the upper cap. We know that at the left end, the forces is calculated in the table because our moment was P times W. If we look at the right end, we see that the axial force is 0 because there's no moment there. And because we cut the web off, we put our little distributed shear flow along the web where it would have had a chance to resist. Now if we want to find the magnitude of Q, we'll just sum our forces in the X direction. We'd find PU minus QW equals 0, and we would find that Q is just PU divided by W. Now if we draw the lower cap, we have the exact same thing, except now we have tension in the lower cap, which means the shear flow is in the other way, and we get the same value of the shear flow. If we draw our web in there, we can see just action and reaction pairs. We know this web is in the same exact shear flow, and we now can draw our caps. Now you'll notice now where before we had no shear flow on our cap, now we do have a shear flow on the web. When we draw that little vertical member on the right side of the beam, we see that that force was applied to that vertical member, and the only thing it's attached to that has vertical resistance is the web. Remember, those caps which have normal stress resistance in this direction have no resistance in that direction because we're assuming that that area is just a tiny little point. But the webs, which have no normal stress resistance, have shear resistance. So all of the resistance here is caused by the web. So we have the force acting on that vertical stiffener, P, and it's resisted by this Q. So if we sum our forces vertically, we'll say P minus Q times H equals 0, and we will find the exact same value of the shear flow as we did working from the caps. If we didn't, we have an error. In fact, we could have just summed forces on this vertical member to calculate the shear flow on the web, and then calculated the change in the force in the caps by just summing up the forces using that value instead of the other value. Then we see that that web is causing the shear flow shown at left, which goes into the wall, and we see that the vertical reaction V is equal to Q times H. And the moment going into the wall is just PU times H, which will be the same as PL times H. Got it? That's how you draw an exploded free body diagram. If you were doing this and claiming credit, you would show magnitudes with proper sig figs and units, and then box that mother. Those are the values we talked about. Got it? Here's one more example. Once again, we have a simple segment. We have axial load. We have a moment on this thing. How do we calculate our stresses? We construct our table, put in our areas, put in our Y positions, calculate our properties and our A and Y bar, calculate our moment of inertia of each piece about the centroid and the total moment of inertia, calculate our stresses, and we can calculate the forces in the caps in the same way. Now this is a pure moment, which means there's no shear, which means the force isn't changing, which means the shear flows will be zero. If this had been generated with a shear, then they would have been different. That's all we've got. Enjoy.